So thinking about discontinuities was a lot easier when we actually had a graph to look at. It's pretty easy to tell when there's a break in the graph. It's a bit harder when you have just an algebraic function. So for example, we have g of x here. It's x squared plus 3x minus 40 over x squared minus 3x minus 10. This is a rational function. Remember that rational functions typically have characteristics such as vertical asymptotes and holes. And so when we want to decide where g of x is not continuous, we want to think about where those things are, the holes, the vertical asymptotes. And so in order to help us out, we are going to factor g of x. So factor the numerator, factor the denominator. Remember this from pre-calculus. So my numerator is x plus 8 times x minus 5. My denominator is x plus 2 times x minus 5. So I see that this factor cancels out, x minus 5. Remember that if a factor cancels out, that means there's a hole there. So at x equals 5, there's a hole in my graph. The other thing I want to look for is where this graph would be undefined and have a vertical asymptote. That would be factors in the denominator that do not cancel out. Factors in the numerator that don't cancel out are x-intercepts, but in the denominator, they're vertical asymptotes. So at x equals negative 2, the 0 of that factor, there's a vertical asymptote. So we say that g of x has at the hole, it's called a removable discontinuity. A removable discontinuity at x equals 5. And the vertical asymptote is an infinite discontinuity. So it has an infinite discontinuity at x equals negative 2. And so we were able to figure these out without actually having to look at the graph, but just remembering this topic from pre-calculus. Now the other thing this problem asked for was the intervals over the function where the function is continuous. So all we're going to do is take the domain of the function, which would have been all real numbers, negative infinity to infinity, and we will remove these places where the function is not continuous. So we will take out negative 2 and 5. So we can say that g of x is continuous on the interval negative infinity to negative 2, union negative 2 to 5, union 5 to infinity. Besides rational functions, another place where you will commonly be asked to determine if a function is continuous is on a piecewise function. So again, we're using that three-part definition of continuity. So remember, first, is the function defined? Second, does the limit exist? Third, do those two values match up? So our first thing we want to find, we're looking to see if this function is continuous at x equals negative 2. So we're going to see, is f of negative 2 defined? And the way I tell that on a piecewise function is I'm looking for where my function, my domain piece has an equals negative 2. Sometimes that's an equals by itself, sometimes it's in an inequality. And so for f of negative 2, I'm going to evaluate at 3x plus 2. So 3 times negative 2 plus 2, and that would give me negative 4. That is defined, I get an answer, so my first step is good. The second thing I want to do is check to see if my limit exists. Remember that with piecewise functions, you probably want to split your limit left and right. So because I'm doing it at negative 2, I see my function is defined to the left as negative 2 squared of x plus 6, and to the right as e to the x plus cosine pi x. Now these functions might look a little bit more complex, but don't get scared about them. All we're going to do is calculate the limits, and we'll try it by evaluating it first. So limit as x approaches negative 2 from the left. I have to choose which piece, and that is the top piece in this case, negative 2 squared of x plus 6. Remember, with limits, all we're going to do, I'm just going to take this negative 2 and I'm going to plug it in for my x. So negative 2 square root of negative 2 plus 6. Sometimes the functions are more complex, but in this case it's pretty easy. So I have negative 2 times square root of 4. which is negative 2 times 2. So my answer is negative 4. Seems pretty good so far. This is matching up. Let's check the limit as x approaches negative 2 from the right. So I'm going to use this bottom piece, e to the x plus cosine of pi x. So e to the x plus cosine pi x. Notice I'm writing this with the variables first because I haven't actually evaluated. Now in my next step, I don't write my limit statement, and I'm replacing the variables with the negative 2. Now let's try to simplify this a little bit. E to the negative second means 1 over e squared. Cosine of negative 2 pi is equal to cosine of 0, which is just 1. Now, I'm not sure offhand what 1 over e squared is, but I do know it would be some decimal value. If I add 1 to it, it's definitely not going to be negative 4. So I don't even have to plug this into my calculator and get an exact answer because I know it's not equal to negative 4. And so since those two limits don't match, then I know that the limit as x approaches negative 2 of f of x does not exist. And therefore, automatically, I know that this function, therefore f of x, let's use the name of the function and make sure you do that and not just call it it, is not continuous at x equals negative 2. That's my answer. I'm going to put a box around it. All right, we'll try the same thing for number 6. We have g of x now. So first thing we're going to check, we're looking at x equals pi. Is g of pi defined? So I know I will plug into the second function. I'm looking for that equal sign for the equals pi, e to the pi, tangent of 3 pi over 4. Now I know you might be struggling to remember your trig values, which you will need to work on if you're struggling with it. You might think of tangent of pi over 4 in the first quadrant, that's positive 1. But in the second quadrant, 3 pi over 4, tangent is negative, so this is negative 1. So that means g of pi is negative e to the pi. Again, that is some number. It's okay. I'm just going to check it off. I don't need to worry about what it is as decimal. Number 2, I'm going to check my limits. Again, it's a piecewise function, so I'm probably going to check my left and my right limits. Limit as x approaches pi from the left is e to the x cosine x. That's my piece to the left of pi. So I have e to the pi cosine pi. And cosine of pi is negative 1, so this is negative e to the pi. Seems good so far. Let's check my right limit. I will be evaluating the expression e to the x tangent of 3x over 4. And so this is e to the pi tangent of 3 pi over 4, which may seem familiar. So I also get negative e to the pi. I see that those match, which means my limit as x approaches pi of g of x is negative e to the pi. So my second step, my second part of my definition of continuity is true. So the third thing I want to check is, did I get the same answers for numbers 1 and 2? And I did. So I will say the limit as x approaches pi of g of x is equal to g of pi. And then let's write our conclusion. Therefore, g of x is continuous at x equals pi. For this last style of problem, it looks kind of the same as the last one. We got a piecewise function here. And what it's asking, though, is trying to figure out, I have these extra constants, m and k. I don't know what those are. And what my goal is to try to figure out what m and k are so that the function is continuous everywhere. So what might help you to think about is what this graph actually looks like. So at negative 1 and for lower x values, my function is 2. At 3, and for higher x values, my function is -2. And I'm trying to think about some function mx plus k, which I know would be linear, that I could use to connect these two to make my graph continuous. I need to figure out what that is. Now in this case, I might be able to actually do that geometrically, but a lot of times you won't be able to. So we're going to try to solve that algebraically. So A, it says what two limits must equal in order for f of x to be continuous at x equals -1. So my left limit and my right limit would have to match. My limit as x approaches -1 from the left, and my limit as x approaches -1 from the right. But let's use the piecewise function here to decide which piece is left and right. So for -1, the piece to the left is 2, and to the right is mx plus k. Same thing has to be true for B. What limits would have to be equal in order for f to be continuous at 3? Same idea, limit as x approaches 3 from the left of something has to be equal to the limit as x approaches 3 from the right of something. And so to the left of 3 is mx plus k, and to the right of 3 is -2. So we're going to keep those limit statements in mind to help us determine the values of m and k. So my first statement from A, if those two limits are equal, let's actually evaluate them. And so I would think about plugging in -1. There's no variable here, and so that means that limit is just 2. On the right side, the limit as x approaches -1 from the right of mx plus k, I'm plugging in -1 for x. So that's equal to -m plus k. Now, right now I can't solve that for any variables, so let's take the second limit statement and see what kind of equation we get. Again, I'm evaluating this limit as x approaches 3 from the left, so I'm just going to plug in a 3m plus k. And for the right, I have -2. So I have two equations, two variables. That means I can use a system of equations to solve this. You could either use substitution or elimination. In this case, I'm going to use substitution because I think it's a little simpler, but feel free to use elimination if you would prefer. So I have 2 equals -m plus k. I'm going to solve that for k. So 2 plus m is equal to k. Now I can take that, it's not my answer, I'm just boxing it to move it, and instead of k, I can substitute in the 2 plus m. So I have 3m plus 2 plus m, because I knew from my first equation that k was equal to 2 plus m. And now I have one equation with one variable, which means I can solve it. I have 4m plus 2 is equal to -2. So 4m is equal to -4. So m is equal to -1. Now I still need to find k. I can use this formula again, k equals 2 plus m. But m is -1, so that means that k is 1. So when I look at this graph then, my m was my slope. This graph has a slope of -1, and my y-intercept would be 1. And so my graph is a little bit off there because my grid wasn't perfect, but you get the general idea. So number 8 is just like number 7. We just have a little bit more complex function. So we've got some kind of quadratic, so a parabola, another line, and then another line. So again, I'm checking at -2 and 3 because that's where my graph splits into different parts. Individually, a parabola and lines would be continuous graphs, so we just have to check to see where they match up. So in order for f to be continuous at -2, I would have my limit as x approaches -2 from the left of something has to equal the limit as x approaches -2 from the right. And let's fill in what those somethings are. So to the left of -2 is kx squared plus m. And to the right of -2 is 4x plus 1. In order for f to be continuous at x equals 3, I would say that the limit as x approaches 3 from the left of something has to be equal to the limit as x approaches 3 from the right of something. So the left of 3 is 4x plus 1, and to the right of 3 is kx minus m. So again, I can use those two limits. The first one I'm going to evaluate at -2, plugging that in for x. So I would have -2 squared times k, 4k plus m, is equal to, evaluating this at -2, so I'd have -8 plus 1, that's -7. This equation here, I'm evaluating at 3, so 4 times 3 plus 1 is 13. That equals 3k minus m. And then I can solve using a system of equations. I want you to do that part on your own, and then you can check your answers. They're not the prettiest. You should get k equals 6 over 7, and m equals -73 over 7.